Hi friends, we were discussing about the stereochemistry of phosphorus compounds, right? So let us continue with that, right? So see, I was talking about pH3, right? So if you see, this compound is optically inactive. Optically inactive. Why it is optically inactive? If you see, this phosphor will be like this. One hydrogen will be here, one will be above, one will be below, right? So if you see, this is the lone pair which is present on phosphor. So if you see, it has got, if I cut like this, all this lone pair, this phosphor and this hydrogen can cut into equal half when I send a plane of symmetry like this. So this is the symmetry, and that plane will pass in such a way that this hydrogen will be mirror image of this hydrogen, right? So this you can take a model and you can check it, in which the plane will cut this lone pair phosphor and hydrogen into equal half, right? So both will be like mirror image of each other, and this hydrogen and between these two hydrogen, this plane will pass like this. So this hydrogen will be mirror image of this. So it has got what it has got plane of symmetry, and also if you see, it has got axis of symmetry. These things you will understand only when you have studied this group theory. Alright, so if I make a video on group theory, there I will explain it so that it will be clear to you. Right. So since these symmetry elements are present in this compound, so this compound will be optically inactive. Right. So scientists what they did, they wanted this optically active compound. Right. So they wanted optically active compound. So what they did, so they expect it is having lone pair. If I attach any A, B and C molecule, then what happens? All are different. A is different, B is different, C is different, and these lone pairs. Since all these are different, this phosphor will become chiral or asymmetric. Asymmetric. Once the phosphor is asymmetric, that will be optically active. They expected like this. So what they did, they went for the search of such compound, right? So they came up with this compound. The compound is phosphor having lone pair attached to methyl CH3. I will write it as Me, methyl, ethyl, and phenyl. Sorry, they took not ethyl, they had this methyl, here benzene ring phenyl, and propyl, right? So you should know methyl. If I write methyl, it is equivalent to CH3. If I write pH, it is equivalent to benzene ring like this. It is attached to something, here it is attached to phosphor like that, phenyl. PR means propyl. Propyl means CH3, CH2, CH2. It is attached to phosphor like this, right? So you should understand, here it will be CH3, here it will be CH2, here it will be CH2, right? So this is propyl. 3 carbon means propyl. 1 carbon means methyl, and this is phenyl. And there will be ethyl also. Ethyl means CH3, CH2. It is attached to something atoms. So we can write it like this also. We will write CH3, CH2 attached to something. Here if you say phosphor, so it means here we have CH3, here it is CH2, right? CH3 and it is CH2 like that. So you should know all this, right? So they came up with this compound. So this compound, they saw that it was optically active. Optically active. Why it is optically active? If you see lone pairs, here methyl I have, here phenyl I have, here propyl I have. All these things are different from each other. So 4 atoms which are different, then that phosphor will be asymmetric. So it will be optically active. Why that compound will be asymmetric? You should know, because here no symmetry elements. No symmetry elements. Means this compound doesn't have any symmetry elements like plane of symmetry, center of symmetry, or axis of symmetry, mirror plane symmetry. All the symmetry absent are absent. So this compound will be optically active, right? Such phosphor we call it as asymmetric phosphor. This phosphor is nothing but asymmetric phosphor we call, right? So for this compound, it is optically active, and in carbon you have said that optically active carbon we do R and S nomenclature, right? So here in stereochemistry, other than carbon, this R and S nomenclature will be done like this. See here. So what we do is, here priority it is phenyl will get 1. This is second priority. This is third priority methyl. Lone pair should be given last priority 4. Right. So the arrow will move as 1, 2, 3 like this. So it is anti-clockwise. So we call it as yes. Right. If it is clockwise like this, then it will be R. Right. So this is the simple nomenclature. But most of the times in these compounds, like other than carbon, they won't ask R and S nomenclature. Just they ask you whether it is optically active or not, or they will ask you geometrical isomerism. They will ask if it is optically inactive. Those things they will ask, right? And some reactions they will ask, which we are going to discuss now, right? So what we discussed now. So we discussed this compound, what it is: methyl, phenyl it is there, propyl is there. This compound is optically active. Sorry, active. So they resolved this compound. Scientists resolved this compound, and they treated this compound with this one, pH CH2Br. Right. Here it means here CH2 group is there, right? So here this lone pair is there. So SN2 kind of reaction. This bromine is a good living group, leaves the system. So what happens? We will get this product: phenyl, methyl, pH, Pr, CH2, pH. And this phosphor, as it gave the lone pair, phosphorus will get a positive charge. Bromine left the system with electron density, so Br minus. So this, it will remain in the solution like this: quaternary phosphorus salt. Right. So quaternary ammonium salt you have discussed, right? In the same way it is phosphonium salts. We call what we can call, we can call them as phosphonium salts. Phosphonium salts, because plus and negative charge, these are nothing but salts, cation and anion, cation and anion. Right. So they saw that this compound, this compound before this compound which was optically active, they did nomenclature, it was S. Plus means it is dextrorotatory. It is used to rotate the right plane, polarized right to right side. So right side means dextrorotatory, we can call dexto, that is represented as plus. Right. So it doesn't mean right side means R only. It doesn't mean that. R and S nomenclature it is done by us, right? But dextrorotatory, rheorotatory, that we will tell by experimental process. If plane polarized right is rotated to right, it is dextrorotatory. If it is rotated to left, then it is leorotatory. It is represented by minus. So this compound, right? So we did R and S nomenclature. We observed that it is yes. So yes, after reaction with this pH2Br, we got this product, phosphonium salt. And here it was again S plus. It means initially it was yes, right? Initially it was yes, and finally after the reaction also it is yes. So here the retention of configuration happened. Retention of configuration. So in exam what they will do, they will give this reaction. They will give the reaction, just they will ask you what kind of reaction it is and everything. You need to tell it is optically active compound and it is S plus. After reacting with this, it will form this phosphonium salt. And here also there is retention of configuration. Both will have S plus and S plus. So after reaction also it is having same configuration. So here retention of configuration happens. Initially yes, after reaction it is yes. So retention we call. What retention happened? Configuration retention happened. So retention of configuration, like that you need to tell it, right? And I told this compound, which compound? This methyl phenyl propyl is optically active. Optically active. What does it mean? Optically active means it is not showing any pyramidal inversion. Pyramidal inversion is absent. Means here no pyramidal inversion. Why it is not having pyramidal inversion? Because this is not converting it into like planar structure. Methyl, phenyl and propyl, like this planar structure it is not going to convert further, like inversion it is not happening like this. Methyl, phenyl and propyl. So such kind of reaction it is not happening, right? Because if you see its energy, the energy is very high. This energy, height and the breadth both are very high for this compound, methyl phenyl propyl. So here no inversion is happening because I told the room temperature energy is 20 kilocalorie per mole. So this energy is not sufficient to cross this barrier energy. So this is the barrier energy which is more than, I don't know, we don't have the exact value for this, but it is more than 20 kilocalorie per mole, which is not there in room temperature. So from here to happen this pyramidal inversion, it is not happening. It is not happening. But if I, however, if I increase the energy by heating or something, if I heat the reaction, if I increase the energy more than this 20 kilocalorie per mole, whether the reaction happens or not, yes, it will happen. That I am going to explain it now. Right. So see, if you see this compound, methyl, phenyl, propyl, and it is lone pair. We saw it is S plus, right? So it was optically active. Optically active, and it is resolved in room temperature because room temperature energy is not sufficient for this pyramidal inversion, so it was optically active. If pyramidal inversion was happening, then in its transition state, like this here in transition state, it will be having planar, so plane of symmetry, it will be optically inactive, right? So but it is optically active because at room temperature it is more stable, right? But what we did heating condition. I started heating this compound, because of which it exhibited pyramidal inversion. So it started exhibiting pyramidal inversion as I started heating, because now I increase the energy more than 20 kilocalorie per mole, right? So I crossed the room temperature and I started heating it. So pyramidal inversion. So what happened? Initially it was only like this at room temperature, right? But when I started heating, it started like pyramidal inversion, and it formed a transition state like this, in which all are in same plane. As all are in same plane, so if I take a plane, I can cut all these into equal half like this. This phosphor, methyl, phenyl, everything. So there is a plane of symmetry. So since it has got plane of symmetry in one of its transition state, this is transition state. So it became optically inactive like this. Further, what happens at heating condition? So it got inverted like this, methyl, phenyl and propyl. So this is only possible in heating condition. So this is the symbol. Heating means we represent like this, heating symbol, right? So they observed that optically active compound, this was optically active compound initially. When they heated this compound, it converted like this. We got the product like this, same methyl, propyl and phenyl, in which its configuration was what? R minus, right? So what do you mean? What did you understand? So nothing much. See, initially it was S plus, which is optically active. After heating, it inverted and we got this R minus. That is the thing. This happened only in case of heating condition. So this will also be asked in your exams. So you have to remember. Initially it was S plus. After heating, it became R minus. So what happened? Inversion, inversion in configuration, configuration happened. So inversion in configuration means S becomes R or R becomes S. S becomes R or R becomes S. That is nothing but inversion we call. Here S plus has become R minus. So inversion of configuration we call. And also we studied like S remains S or R remains R. That we call it as retention. Retention in configuration. These things you should know, right? So retention in configuration, S remains S, R remains R. Inversion means S becomes R, R becomes S. So here if you see above, initially it was S plus, now it has become R minus, right? So this is nothing but inversion in configuration. These reactions they will ask, right? So one more reaction, let me tell it. So what is this? This is phenyl methyl propyl, or phenyl like propyl, and lone pairs are there. It is S plus, right? So if I add some oxidizing agent like hydrogen peroxide H2O2, what happens? I will get this thing. Everything remains as it is. Phenyl will remain, propyl will remain. I will get oxide, right? So that is nothing but phosphine oxide. The thing is phosphine oxide, we call it is phosphine oxide. So here it is S plus, right? So it is S plus. After this oxidizing agent H2O2, I got this phosphine oxide. If you see its configuration, it is again S plus. Sorry, it is again S plus. What does it mean? So S remained S after reaction. So it is retention of configuration. So here when we add any oxidizing agent, there will be a retention in configuration. So from phosphine we converted into phosphine oxide, adding oxidizing agent in which the configuration remained same. S remained S, so it is retention in configuration. So these are the few reactions you need to remember, right? Because they will ask these reactions in exams. So here it has been, you have to remember all these things, right? Right. So once we discussed these reactions, let us now discuss few more concepts, right? So we were discussing upon phosphine oxide, right? So this is our phosphine oxide. So let me take methyl, ethyl, and phenyl. So this is one of the phosphine oxide. What phosphine oxide, right? Because here all our four atoms are different. Here methyl I have, here ethyl I have, here phenyl I have, here oxygen I have. Since all four atoms are different, the phosphor is asymmetric. Since phosphor is asymmetric, it is not having any plane of symmetry, center of symmetry, axis of symmetry, mirror plane symmetry. All the symmetry absent are absent. So these compounds will be optically active, right? These things we have studied so lot more times, right? So this is optically active compound. But the thing is, this is optically active, no doubt. But in acidic medium, it will racemize. It will racemize. What does I mean is, see, this is my oxide. Here I have methyl, ethyl, and phenyl. Acidic medium means H plus will be there and water will be there, right? So that is acid dissolved in water. If we add HCl in water, we will get H3O plus, right? So we can write H3O plus or H plus bar H2O, which I have written above, right? So if that is the thing, this H plus will react with this, so it will, and it will take its electron density. So what happens? POH it will form. Here we have methyl, here we have ethyl, here we have propyl, and phosphor gets positive charge. But in reaction, water will be there, as I have shown here. So that water will react with phosphor, and I will get this product. Which product I will get? Phosphor will be here like this, OH here and OH here. That OH has come from water, right? Other things remains as it is, methyl, ethyl, and this is what? Phenyl. So all these will be in same plane. All these three will be in same plane. Whereas this OH will be above the plane, this OH will be below the plane. If I take a plane, right? So this is the plane if I take, if this is the plane, and if I pass it with this molecule, what happens? This phosphor will be equally halved, this methyl will be equally halved, ethyl, phenyl. So this plane will pass like this. Within these four atoms it will pass and it will half them. And this OH will be mirror image of this, because plane is passing like this. It is cutting all these things. So all these into equal half, and this OH will be mirror image of this. So it has got now plane of symmetry. So it will become optically inactive, right? So what happens optically inactive? It has happened, right? So in this way it will racemize, right? So initially it was optically active, but in acidic medium, so it will convert into optically inactive, and it can racemize. Racemize means R becomes same amount of S can be happened because of water medium. So what happens here, initially it was R like this, methyl, ethyl, phenyl. After this H plus in water, it can become like this, methyl. Here let me write phenyl, and here ethyl. Initially let us assume that it is R, now it is S. Both will be in equal amount, so it will racemize only in acidic medium, right? So this kind of reaction they will ask you, right? So you need to remember this thing also, right? So racemization happens in presence of water medium. So this is the thing. Now let us see few more concepts of this. So we discussed about this phosphine oxide, right? Phosphonium salts. What is this phosphonium salt? If I have like a phosphor A, B, C and lone pair, if I react with any of the electrophile uh, like ethyl bromide, I have CH3CH2 Br. So here SN2 kind of reaction happens. If it is R, it will remain R only after reaction also. These things we have studied within this class only. And CH2, right, this I will get ethyl, CH2 CH3 I will get, right? So if it is R, it will remain R only, right? If it is R plus, it will remain R plus. So retention RR, after reaction retention of configuration happens. But here the phosphor lone pair have reacted, so this phosphor gets positive charge, and here Br minus is there, so Br minus will be there in the solution like this. So cation and anion present within same two ether, we call it them as like phosphonium salt we call, right? And this phosphonium salt are optically active, because see initially it was R plus, and after forming this phosphonium salt it is again R plus. So R plus means it is also optically active, and this is also optically active, right? Because this phosphor is chiral, because it is attached to four different atoms, A, B, C and this ethyl, all are different, so it is optically active. You may ask if all atoms, not all atoms, if I have this salt like this methyl plus here ethyl, and here hydrogen, that will be optically inactive, because this hydrogen two atoms are same, then they will be having plane of symmetry. If you see, then that I have shown it in the first class. If you could imagine with this also, then you can tell that it is will be optically inactive, right? So this is how it is. So let us see. So some of the optically active phosphonium salt, let us see, right? And anion will be there along with that, right? So let us see that. So here I have few examples. For example, this one. So this is what, this is benzene ring, right? And here we have phenyl, and here we have C6H4OH at para position, right? So phosphor will be having Br plus, phosphor plus and Br minus. So this is optically active phosphonium salt it is, right? So can you understand what I have written here? C4H4OH para means here we have benzene ring like this, right? Para position we have OH group, and here we have phosphor group, right? So for phosphor this is para, so it is para OH, and molecular formula if you see it is C6H4, right? So they will write it like this, right? So again in future if I write anything like this, you should be able to imagine the structure like this, right? So this is the one of the salt which is optically active, right? Let me give you one more salt. So these were the salts which were discovered by so many scientists. So in books what they will do, they will give so many names for these compounds. So many names means name of the scientist they will give, whether they resolved or not, in the year they will give, the name of the compound they will give, right? So it makes you confusion, so I am not giving all those things. So here phosphor is having plus charge, iodine is the anion, so it is nothing but quaternary ammonium salt, and it is optically active. Optically active. You will ask, sir, here also same atoms are there, here also same atom. Yeah, atoms are same only. You will assume that all are same. It will be having any plane of symmetry or anything, but here no plane of symmetry will be there, because it will be like this. Two of the bonds will be above the plane. So for example, if I have like this will be above the plane like this, and this will be below the plane, right? Below the plane, because of which there will be no plane of symmetry or anything, right? So because of which there is no plane of symmetry, center of symmetry, no any symmetry elements. So the symmetry elements are absent. So this phosphor becomes asymmetric. Asymmetric phosphor. So asymmetric phosphor means the molecule itself becomes asymmetric here. Asymmetric means no symmetry elements are there. So the molecule, the whole molecule itself becomes asymmetric. So asymmetric means it will be optically active. Optically active means what? Asymmetric means no plane of symmetry, center of symmetry, all these symmetry elements are absent. So a molecule is asymmetric, so it is optically active compound, right? So these are the few phosphorus thing which are optically active, right? So we have left with two more reactions. Let us discuss about those reactions, then we can conclude this stereochemistry of phosphor. So here I have ethyl, methyl, phenyl, and it is CH2PH, right? So this is phosphor I plus, and we have anion, that is I minus, right? So this, if I have this compound, right? I hope how you know how we got this compound. This is nothing but reaction between this one, methyl, ethyl, phenyl. And I reacted with this, which one I have? Yeah, CH2PH I have. Okay, pH, CH2Br. If I react, this is nothing but SN2 reaction like this. Br will leave the system. Here I minus, let me take I, so that I will get anion I minus. So this product we will get. So this reaction we have studied, in which if it is R, after reaction we will get R only. So retention of configuration happens. The reactions we have seen above only, right? So this is retention. Further, what happens to this compound, that is salt, phosphonium salt, if I add any NaOH base, so NaOH base means OH minus will be there, anion. So we will get oxide, right? So we will get oxide, in which everything will be same as it is pH. Here we have methyl, and we'll get oxide, phosphine oxide, plus pH CH3, right? Here it was pH CH2, right? pH CH2 has become pH CH3. If you see reaction, I told it was R. Now after when we react with OH minus, it has become oxide, phosphine oxide, and its stereochemistry, if you see, it is S. So from R to S, conversion means the inversion in stereochemistry happening. Inversion in stereochemistry, right? So these reactions you should remember. They will ask you, right? So initially of this reaction, it was R. After this reaction, we got this product called phosphor, called salt. We got, which is retention in configuration, because all remain R. But when we reacted with NaOH, here the OH minus, this CH2 pH has gone out as pH CH3, right? Toluene, it has gone out, and we have formed this oxide, phosphor oxide. If you check the stereochemistry, initially it was R, now it has converted to S. So from R to S means inversion in stereochemistry happened, right? So this reaction we call it as inversion in stereochemistry, right? So this is the thing, right? So these were the reactions. I have left with one more reaction, right? No. I have discussed about this. So this reaction is given in the year 1965, right? So by the scientist me Evin, Evin, right? So this is the reactions were of phosphor oxide. So this stereochemistry you need to remember. What happens with NaOH, what happens with oxidizing agent, what happens with any SN2 kind of reaction, whether stereochemistry changes or not, inversion, rotation, these things only they will ask. So you should remember all these reactions. I hope I have made you clear. So if so, if you liked the video, give me the like button. If you are not subscribed, do subscribe my channel. And if you liked these videos, please share with all your friends and tell them, share with their friends, subscribe and all. Right. Thank you.